Bismillahirrahmanirrahim. I am Dr. Syed Azhar. In this lecture, we will study spanning sets. For example, we have a set of two vectors, say u1, u2, such that u1 is 1, 0 and u2 is 0, 1. Let us denote this set of two vectors by symbol S. Now, we are interested in those vectors which can be written as a linear combination of these two vectors. So, for example, we have 2, 3. So, 2, 3 can be written as 2u1 plus 3u2. That is 2 into 1, 0 plus 3 into 0, 1. Similarly, minus 2, 5 can be written as minus 2 times u1 plus 5 times u2. 3 by 2, comma 7 minus 7 can be written as 3 by 2 times u1 minus 7 times u2, and so on. So these are the vectors which can be written as a linear combination of these two vectors. Let's create a set consisting of such vectors. Say that is u is equal to 2, 3 minus 2, 5, 3 by 2 minus 7 and so on. Now, we say that this set is a spanning set for this set. Since each and every vector of this set U is a linear combination of these two vectors, so we say that this set S spans U, that is S spans U. So this is the main basic idea of a spanning set. So the definition of a spanning set is, let V be a vector space. Say this collection of vectors is a vector space, then the given vectors u1, u2 up to um are said to span vector space V, or to form a spanning set of vector space V if each and every vector of the vector space is a linear combination of the given vectors u1, u2 up to um. And for linear combination, we have this equation x1 u1 plus x2 u2 plus x3 u3 up to xm um is equal to vector u. Basically, in linear combination, we express some specific vectors in the linear combination of the given vectors u1, u2 up to um. If each and every vector of a given vector space is a linear combination of these vectors, then we will say that S spans V, and the collection of these vectors denoted by S will be known as a spanning set for a vector space V. In this example, three vectors u1, u2 and u3 are given from the R³ space. And we have to show that the collection of these three vectors S is a spanning set for this vector space R³. Means S spans V. We have to show that S spans V. Since it's very difficult to check each and every vector of a vector space, so that's why we need to show that an arbitrary vector from the R³ space, that is U equals ABC, is a linear combination of vectors u1, u2 and u3. That is, the linear combination of u1, u2 and u3 will be x1 u1 plus x2 u2 plus x3 u3 equals this arbitrary vector u. In linear combination, this u was some specific vector, but here it's an arbitrary vector. Now put the values of u1, u2 and u3, multiply x1 with 1, 0, 0, x2 with 0, 1, 0, x3 with 0, 0, 1. On the right side, we have this arbitrary vector which is a, b, c. And add these matrices, we will get x1 equals a, x2 equals b, x3 equals c. This shows that this vector ABC is equal to A into 1, 0, 0 plus B into 0, 1, 0 plus C into 0, 0, 1. This ABC is actually an arbitrary vector this one is u1, this one is u2, and the third one is u3. This shows that u is a linear combination of u1, u2, and u3. Since u was an arbitrary vector, so it means each and every vector of the vector space R cube can be written as a linear combination of u1, u2, and u3. Hence, this collection S is a spanning set, and this collection spans the vector space R cube. In this second example, u1, u2, and u3 are given from the R cube, and we have to show that the collection of these three vectors, say S, spans the whole vector space R cube. Similarly, we need to show that an arbitrary vector, say u, which is abc, from R cube is a linear combination of these three given vectors, that is x1 u1 plus x2 u2 plus x3 u3 equals u. Put these three vectors u1, u2, and u3 and then multiply x1 with 1, 1, 1, x2 with 1, 1, 0, x3 with 1, 0, 0, and add these three matrices. We will get x1 plus x2 plus x3, x1 plus x2, x1 equals ABC. From this system, look at the third row. Third row gives us x1 equals C. From the second row, we get x1 plus x2 equals B. Substitute the value of x1, we will get x2 equals B minus C. From the from the first equation, x1 plus x2 plus x3, here substitute the values of x1 and x2. C will be cancelled with C, and shift B on the right side, we will get A minus B. Now look at the values of x1, x2, and x3. These are finite numbers because A, B, C are the components of this R cube, means A, B, C itself are real numbers. So x1, x2, and x3, these are also real numbers. Now put all these three values x1, x2, and x3 in this expression, in this equation. We will get u is equal to c into u1 plus b minus c into u2 plus a minus b into u3. Since this vector was an arbitrary vector from R cube, so each and every vector of R cube is a linear combination of these three vectors. Hence, this collection S spans R cube, and this collection S is known as a spanning set. For example, we have to write this vector in the linear combination of these three vectors. There are two ways to write this U in a linear combination of these three given vectors. The first way is to write these given vectors u1, u2, u3 and this specific vector in this equation and solve this system. It will take some time, but in this example second part, already we have formulated a general expression for an arbitrary vector to be written as a linear combination of these three vectors, which is u is equal to c dot u1 plus b minus c into u2 plus a minus b into u3. Now clearly compare that arbitrary vector which was a, b, c with this equation, with this vector. So it will give us a is equal to 5, b is equal to minus 6 and c is equal to 2. Now substitute these three values in this equation. We will get u is equal to c means 2 dot u1 plus b minus c. The value of b is minus 6 minus the value of c is 2 into u2 plus a minus b. The value of a is 5 minus b, and the value of b is itself negative, so that minus will make it positive, plus 6u3. So u will be 2u1 minus 8u2 plus 11u3. So u can be written as this linear combination of u1, u2 and u3. If you solve this equation, you will get this result. So you can follow either this way or this equation. In this third part of example, U1, U2 and U3. U1 is 123, U2 is 135 and U3 is 159 are given from the R cube space. Let S consist of these three vectors U1, U2 and U3. We have to show that whether this collection spans R cube or not. So similarly, we need to show that an arbitrary vector u from the vector space is a linear combination of these three given vectors. So we have to write this arbitrary vector in these three given vectors linear combination. Now put these three given vectors and this specific vector in this equation. Multiply x1 with 1, 2, 3, x2 with 1, 3, 5, x3 with 1, 5, 9 and add these matrices on the left side. We will get, from this matrix system we can obtain x1 plus x2 plus x3 is equal to A, 2x1 plus 3x2 plus 5x3 is equal to B, and similarly from the third row we will get this third equation. Now we have to solve this system. So first of all we will write this system in its augmented matrix form. After that we have to transform this augmented matrix into echelon form. Since this one is our pivot entry, so we have to eliminate 2 from the second row and 3 from the third row. That's why R2 minus 2R1 and R3 minus 3R1 are our desired row operations. First of all, we will use R2 minus 2 times R1 operation. First row will remain same and 2 times of 1 gives us 2 and subtract that 2 from this 2, we will get 2 minus 2 equals 0. 2 times 1 gives us 2 and subtract that 2 from 3, we will get 3 minus 2 equals 1. 2 times 1 gives us 2 and subtract that 2 from 5, we will get 5 minus 2 equals 3. 2 times of A gives us 2 and subtract that 2A from this B, we will get B minus 2A. Similarly, in the third row we are using R3 minus 3 times R1 operation. So 3 times 1 gives us 3 and subtract the 3 from this 3 of the third row, we will get 3 minus 3 equals 0. 3 times 1 gives us 3 and subtract 3 from 5, we will get 5 minus 3 equals 2. 3 times of 1 gives us 3 and subtract 3 from 9, we will get 6. 3 times of A gives us 3A and subtract that 3A from C, we will get C minus 3A. Here, these are the two pivot entries. Now we have to eliminate 2 from the third row. And for this purpose, we will use second row. So the first row will remain same, the second row will remain same, and in the third row we will use R3 minus 2 times R2 operation. And this will give us 2 times 0 gives us 0 and subtract that 0 from this 0, we will get 0 minus 0 equals 0. 2 times 1 gives us 2 and subtract that 2 from this one, we will get 0. 2 times of 3 gives us 6 and subtract that 6 from 6, we will get 0. 2 times of B minus 2A will give us 2B minus 4A and subtract this value from C minus 3A. We will get C minus 3A, and due to subtraction the sign of 2B will become negative and the sign of minus 4B will become positive. 4A. Now simplify this one. This one will give us C minus 2B and minus 3A plus 4A will give us plus A. Now, if this value is not 0, then the rank of coefficient matrix and the rank of augmented matrix will not become equal. This will show that rank of augmented matrix is greater than rank of coefficient matrix, and in this case we obtained an inconsistent system. So that's why this collection S does not span the whole R cube. Now these are the important remarks related to spanning set. If the collection S spans V, then this new collection is obtained by incorporating an extra vector in the existing spanning set. For example, we know that S is equal to 1, 0 and 0, 1. This collection spans vector space R square, and the new collection say S star, which consists of these two vectors as well as some other vector, say 1, 2. Then this new collection will also span the same vector space R square. In the second remark, if this collection S spans V and this collection consists of a vector which is a linear combination of the other vectors, then you can remove that vector from this collection S, and that is the vector. Suppose the vector uk is a linear combination of the sum of the other vectors, then you can remove that vector uk from S, and this new collection will also generate the same vector space. This is our second remark. In the third remark, if this collection spans V and if this collection contains a zero vector, then you can also remove the zero vector from the spanning set, and the new spanning set will be S minus 0 vector, and that new collection will also span the same vector space R cube. This is the end of today's lecture. Feel free and ask question in the comment section. I will reply inshallah. Thank you.